Let us consider the situation where we have two parallel plates. They are located at a distance h apart. So the gap between the two plates is h, and one of the plates moves with a velocity with respect to the other. So for generality, we can assume that the top plate moves at a velocity u with respect to the bottom plate. This action is essentially a combination of, not a combination, this is essentially shearing, and this is more common than you think. So if you consider two big journal bearings, so there is a fixed cylinder like this. There's a fixed cylinder like this, and there's another cylinder like this. So the fact that they're eccentrically placed means that when this begins to rotate, there is fluid flow between this small gap. So the fluid otherwise is not flowing, but if you zoom into this location, so if the rotation direction is like this, if you zoom in, you have the top plate like this, you have the bottom plate like this. So the diameters are quite large compared to the gap. So if you zoom in, it will appear that the gap is almost comprised of two parallel plates. Well, the fact that it does have a curvature, it does matter, but for the analysis of this location, it does appear that the top plate is moving at a certain velocity with respect to the bottom plate, which is grounded. So this kind of flow configuration is called as a Couette flow. So in in addition to this, the plate being dragged, you can have a pressure driven component as well. That is, additionally, you can have a pressure which drives the flow. So minus del P star del X can also additionally act in combination to U to drive the flow. So what we will be analyzing is a combined pressure driven Couette flow. Let us write down the governing equations for this. So once again, the continuity equation or the incompressible condition is this. So once again, we consider fully developed flow so that del u del x is 0, or rather any gradient in x directions are 0, and we consider that the walls are impenetrable. That is, the velocity field cannot exist in this direction. So at the walls, we will have u equal to 0 and v equal to 0. These are consequences of no slip and no penetration boundary condition. So the governing equation in the x direction and the governing equation in the y direction. So now we will make use of all the assumptions in order to simplify these equations. So apart from being a fully developed flow, we assume that the flow is steady. So if the flow is steady, these terms will vanish. So right away, if it's a fully developed flow, del u del x is 0. So del u del x will be 0, and that implies del v del y will be 0. And if this is true, v equal to constant. I mean, v could be only a function of x, but because it's a fully developed flow, v cannot be a function of x. So v is a constant, and because v equal to 0 at the walls of the domain, that constant is equal to 0. So v equal to 0 everywhere. So it becomes a unidirectional flow. There is no other component of flow apart from the flow in the x direction. Okay, so it's a unidirectional flow. So now because the flow is steady, this term vanishes, this term vanishes. Because it's a fully developed flow, this term vanishes. Because v is 0 everywhere, this vanishes, this vanishes. Okay, this vanishes and this vanishes. Now because the flow is fully developed, this also vanishes. Because v equal to 0, this vanishes. So finally what we have is from the x momentum equation, 0 equal to minus del p del x plus mu del 2u del y2, and from the y momentum equation we have 0 equal to minus del p del y. Once again, I am not writing down the gravity component because that can be written down in terms of the modified pressure P star equal to P plus rho gy. So we can simply make them stars. So P star is the modified pressure. So this implies P is only a function of x. Okay. So this equation can be simplified to minus dp star dx, and because u is only a function of y, because it's a fully developed flow, this becomes d2u dy2. So the Gurney equation is the same as the plane Poiseuille flow, but the key difference will be in the boundary condition. So the boundary condition will be, so if I choose the coordinate system over here, so at y equal to 0, u equal to 0 by no slip, and at y equal to h, u equal to capital U, and this is also by no slip. So the no slip boundary condition implies that the relative velocity of the fluid with respect to the boundary has to be 0. So if the relative velocity of the fluid with respect to that particular boundary has to be 0, it means that the absolute velocity of the fluid at the top wall has to be equal to capital U. So this is also a consequence of no slip. So now we have to solve this differential equation subjected to this boundary condition. So let us see. So dp star dx is equal to mu d2u dy2. Now once again, because p is only a function of x, right? So each has to be a constant because this is a function of x only, and on whatever is on the right hand side is only a function of y. So each of these things is equal to a constant. As in the previous case, if dpdx is constant, then p will be a linear function of x. Okay, p will vary linearly, so along the channel length p will go down linearly. So if this is x, this is the profile for pressure. So regardless of that, dpdx will be a constant, so we can directly integrate this expression itself without worrying about what this is. We can all keep in mind that this will be a constant. So 1 upon mu dp star dx is equal to d2u dy2. So du dy will be equal to 1 upon mu dp star dx times y plus c1, and u is equal to 1 upon mu dp star dx y square, so 2 goes over here, plus c1y plus c2. this is the expression for the velocity. Now for the first boundary condition, at y equal to 0, u equal to 0. So 0 is equal to 1 upon 2 mu dp star dx. So y is 0 plus 0 plus c2. So c2 becomes 0. And for this boundary condition, at y equal to h, u equal to capital U. So capital U is equal to 1 upon 2 mu dp star dx h square plus c1 h, because c2 is 0. So c1 is u minus 1 upon 2 mu dp star dx h square, and then you have to divide everything by h. So this h square becomes simply equal to h. So now we can find out the total. We can substitute this constant in the function and find out an expression for the velocity. So it becomes 1 upon 2 mu dp star upon dx y square plus c1y. C1y means this times y, so it is minus 1 upon 2 mu dp star dx hy, and this other term plus u y upon h. So we can simplify this as minus 1 upon 2 mu dp star dx h square. So this will become y upon h, and this will become minus y square upon h square, and this will become plus u y upon h. So finally the velocity, so I can call this velocity as up, that is the velocity because of the pressure driven flow. So u becomes equal to up y upon h minus y upon h squared plus capital U y upon h. So this is the velocity profile. So naturally, when the pressure gradient is 0, then up becomes 0. So the velocity profile simply becomes capital U y upon h. So this solution itself is the Couette flow profile. And as you can see, this velocity profile is linear. That is, it is something like this. So the velocity over at this location is capital U. Then it linearly reduces and becomes 0 over here. Now you can go to MATLAB or whatever software you like, and you can plot this for different values of UP. In fact, we can make everything dimensionless by dividing everything by UP. So rather we can divide everything by capital U. So U by capital U, this will be UP upon capital U y bar minus y bar squared plus y bar, where y bar is equal to y upon h, is the dimensionless y coordinate. So this can be written as u bar, this can be written as up bar, this is y bar minus y bar square plus y bar. So up bar is actually up upon capital U, which is the ratio of the pressure driven component of the velocity to the Couette component of the velocity. So depending on which term is dominant, you will obtain different flow profiles. So if the flow is dominated by UP, that is if UP bar is quite large, then you will tend to see a parabolic profile rather than a linear profile. But if the plane Poiseuille component, that is UP, is quite less compared to U, capital U, then you will obtain more or less a linear profile. I'll just draw some profiles. I mean, obviously these are not computer generated. So in the absence of any pressure driven flow, this will be the profile. So these are just like schematics. But if there is a pressure driven flow, then on top of this, there will be, there could be a flow like this. If the pressure gradient is in the opposite direction, so this is for dp dx negative. That is, it is driving the flow in the positive x direction. If dp dx is positive, then you will obtain something like this. This is dp dx positive. So in the case of combined flow, there is obviously a point in the flow where there is a maximum velocity occurring, or there can be a minimum velocity occurring. Let us find that value out. So du bar dy bar is equal to up bar 1 minus 2y bar plus 1. So when is this 0? It is 0 when, so let me just rearrange the terms. So in order to find the maximum or the minimum velocity, this has to be equal to 0. So what do we have? 1 upon up bar is equal to 2y bar minus 1. So 1 plus up bar upon up bar upon 2. So this will be the location of the extrema of the velocity. Okay. What is the wall shear stress? The wall shear stress for such a problem can be found out using the expression for the shear stress, which is mu del u del y plus del v del x in general. But because in this case the y component of velocity is 0, this vanishes and this simply reduces to mu du dy, because u is a function of y only. So this is mu upon capital U du bar, because u bar is u upon capital U, upon dy bar times h, because y bar is equal to y upon h. So this is sorry, this u should be on the numerator. So it is mu capital U upon h du bar upon dy bar, and du bar upon dy bar we can simply write down the expression. This is up bar times 1 minus 2y bar plus 1, and we have to evaluate all this at, so tau wall will be at y equal to 0. So at y equal to 0, so we have mu capital U by h up bar, so this is plus 1. At the top wall we will substitute y bar equal to 1, so you get the idea. So using this we find out the expressions for the wall shear stress. In case the up bar component is 0, that is there is no pressure driven component, the wall shear stress, it simply becomes equal to mu u upon h. I mean this becomes 0, so only 1 remains. So this is simply the shear stress for a linear profile. And as you can imagine, if you have a linear profile, the slope is constant throughout the domain, and so this is the shear stress everywhere. This is the value of the shear stress everywhere. So let us look at an example. So it is given that we have two parallel plates and water flows between these two plates. So these plates are infinite width in the z direction. So it is given that the lower plate moves towards the left at a speed of 0.3 meter per second. The plate spacing is 3 millimeter and the flow is laminar. So the question is, what is the pressure gradient? So what is the pressure gradient that must be maintained in this between these two plates, across these two plates rather, in order to have a zero net flow? Okay, in order to have a zero net flow, what is the pressure gradient required? Okay, so in fact, we can make use of the solution that we have done above also. Simply integrate over the area. It doesn't matter if it's going in the negative direction or all that. We can simply attach a coordinate system like this. We can simply attach a coordinate system and this becomes equivalent to whatever we have analyzed so far. But anyway, let us not skip the steps or let us not do all those kinds of coordinate transforms. We can write down mu d2u dy2 is equal to dp dx, but dp dx we know is going to be a constant. So upon solving this, I'm going to write down the boundary conditions. Right, at y equal to 0, u equal to minus capital U, where capital U is equal to 0.3 meter per second. At y equal to h, so h is basically 3 mm, u is going to be equal to 0. So these are the boundary conditions. So we have du dy is equal to 1 upon mu dp dx times y plus c1, and u equals to 1 upon 2 mu dp dx y square plus c1y plus c2. So using the first boundary condition, so c2, so 0 is equal to minus capital U. So sorry, at y equal to 0, u equal to minus u, so minus u is equal to 0 plus 0 plus c2. So c2 is equal to minus capital U, and using the second boundary condition, 0 is equal to 1 upon 2 mu dp dx h square plus c1h. So c2 is minus u. So from this we obtain c1 equal to u minus 1 upon 2 mu dp dx h square, and there will be a divided by h. So c1 comes out to be u by h minus 1 upon 2 mu dp dx times h. So then if we combine if we use these two constants in the expression for the velocity, so the velocity comes out to be u equal to 1 upon 2 mu dp dx y square plus c1 y. So c1y will become u y upon h minus 1 upon 2 mu dp dx y h plus c2. So c2 is simply minus u. So this is 1 upon 2 mu dp dx y square minus yh plus u y upon h minus u. So now we can integrate this over the entire channel. So this is not the coordinate system. We have used this coordinate system only. So Q is equal to integral U dA. So if we assume the width into the paper as W, so it will be U W dy. So if we assume a unit width, this W can be simply removed. So remember that these calculations are all per unit width. So this integration will be from 0 to h. So what do we have? So it's 1 by 2 dp dx. So this will be y cube by 3 is going from 0 to h. So this will be h cube by 3. This will be y square by 2 times h. So this will be minus h cube by 2 plus u upon h. So y square by 2. So this will be x square by 2 and this will be y. So this will be h. So this is equal to, so this will be equal to 1 upon minus 1 upon 6. So minus 1 upon 12 mu dp dx h cube plus, so this will be uh upon 2 minus uh. So this is minus uh upon 2. So if this flow rate has to be equal to 0, right, then the pressure gradient comes out to be minus of upon 2 times 12 mu upon h cube. Yeah, that's it. So this becomes minus 6 mu u upon h square. So if we plug in the values, so it is minus 6. So time the viscosity of water at 60 degrees Celsius. So the entire problem is mentioned that it is at 60 degrees Celsius. So quite naturally it's for some kind of a journal bearing. So the viscosity is given as 4.7 into 10 to the power minus 4 Newton second per meter square times the velocity is 0.3 upon h square. So the gap is given as 3 millimeter. So it is 3 times 10 to the power minus 3 meter square. Let me just plug in these numbers into my calculator. So this becomes minus 6 times 4.7 times 1 minus 4 0.3 divided by 3e minus 3 squared. So it comes out to be minus 94 Pascal per meter. So essentially it means the pressure gradient is negative, meaning the pressure gradient would act in this direction. Okay, it's a negative pressure gradient. So minus dp dx is essentially 94. So minus dp dx acts in this direction. So the plate being pulled tries to have a velocity profile in this direction, but the pressure gradient tries to have a velocity in this direction. So it would be something like this. Okay, so the volume in the negative direction and the volume in the positive direction would be balanced. Now having said this, if you do have a situation like this, there is no guarantee that the flow will remain stable. Okay, on the one end you have a plate being pulled in this direction, on the other end you are sort of trying to push fluid in the other direction. So it's not always a stable configuration. So this is the direction of minus dp dx, this is the direction of u. So if you have fluid, you can imagine that the fluid is trying to overturn. So the assumption of unidirectional flow, it need not be always maintained, and it can lead to a flow instability. So flow instability is something in which you have a flow configuration, but the flow configuration is sort of unstable to certain disturbances. And I say certain disturbances because it is not unstable to all disturbances. It is unstable to disturbances of a certain wavelength or a certain frequency. So if this happens, then the flow will break up into various kinds of secondary flows. It can in fact become turbulent. So one mechanism by which such a kind of counter flow. So this flow is one flow is being dragged in this direction, one flow is pushed in that direction. So it leads to the formation of a Kelvin Helmholtz instability. And this kind of instability can be seen in the formation of clouds. So there will be such kinds of weird structures. I mean, of course, I'll put the image while uploading, but it leads to something like this. In fact, let me look it up. Let me paste it over here. Yeah. So now that we have the appropriate credit to the author, so this is one example of the Kelvin-Helmholtz instability in which the flow on the top of these clouds is happening in this direction, but on the bottom of the clouds is happening in this direction. That leads to, so if everything were to be okay, the flow would be simply like this. But because there's a rotationality, it tries to overturn. Okay, it tries to overturn. So these kinds of patterns are found all over the universe. In fact, you can look up the images of the giant storms in Jupiter, on the surface of Jupiter, and you will see such kinds of patterns. So on Jupiter, what really happens? So let me dig up an image of that also. I need to credit the author as well. Yeah. So this image is courtesy ESA, European Space Agency. So you can focus on this. Okay, over here, over here, in fact everywhere, even here. So basically these are parallel layers of fluid in which one fluid is going one direction. So one layer of fluid is going in this direction while the other layer of fluid is trying to go in the other direction. So it leads to a shearing at the interface, and that leads to instabilities. Okay, so this kind of unidirectional flows act as the base. Okay, so these are whatever we have studied so far. So these are also often referred to as base flows. So in base flows, you don't consider this, and then you can perturb a base flow and see how that equation evolves in time. So far we have considered analysis of a plane Poiseuille flow and a Couette flow. Yeah. So this coordinate is the z coordinate, this coordinate is the r coordinate, and the theta coordinate is in this plane. Okay. So this is a cylindrical polar coordinate system. So the continuity equation in this cylindrical polar coordinate system looks something like this. So 1 upon r del r of r vr plus 1 upon r del theta of v theta plus del z of vz is equal to 0. So this is basically this expression is the divergence of velocity equal to 0. So it's an incompressible flow. It's constant density flow. So when we assume that the flow is fully developed, So when we assume that the flow is fully developed in this particular case, del Vz del z would be equal to 0. That is, the z component of velocity is invariant in the z direction. You can take any cross section you want and you would have the same velocity, provided that the flow is fully developed. Okay, provided that the flow is fully developed. So once again, like the plane Poiseuille flow, you will expect that after a certain distance from the entrance, there will be a merging of the two boundary layers. So after the merging of the two boundary layers, so this is the core, and after this spot, we have the fully developed regime. So in the fully developed regime, del Vz del z is equal to 0. Now, we also assume that the flow has no swirl. So no swirl, meaning there is no component of velocity in theta direction. Okay, there is no component in theta direction, and we can assume that the flow is axisymmetric. So if the flow is axisymmetric, then del theta would be equal to 0. Note in mind that axisymmetric and no swirl are completely different assumptions. We can have v theta non-zero, so v theta may not be 0, but the problem can still be axisymmetric. Okay, if we have v theta not equal to 0, and if we have a constant v theta, the problem is still axisymmetric because of the simple fact that if you look at the problem at any theta, you can look at it at any theta, right? The problem is invariant under rotation in theta. So the problem can be antisymmetric, but rather the problem can be asymmetric and still have no swirl. But that is, so these two are mutually exclusive. Okay, they are not one and the same. One does not imply the other. Okay, so now let us invoke these approximations into the continuity equation. So if this is 0, this particular term drops out. Because of axisymmetry and no swirl, this particular term also becomes 0. So from the continuity equation, we have 1 upon r del r of r vr. Hey, apologize for that. So del 1 by r del r of r vr is equal to 0. So this implies that r vr is equal to constant. That is, r times vr is not a function of r. Okay, and the fact that vr at the walls of the tube will be equal to 0. So vr equal to 0 on walls, that is due to a no penetration boundary condition. And so that implies that vr has to be 0 everywhere. The same logic behind what we had studied in the plane Poiseuille flow. So vr equal to 0 everywhere. So VR won't be 0 everywhere if the walls are porous, say, so there is some flow coming in through the walls and so on. So proceeding, so the corollary of this is also that Vz is the only non-zero component. Vz is the only non-zero component. Everything else is 0. And through this condition, del z equal to 0. So Vz is not a function of z, and also by axisymmetry, Vz is not a function of theta. So all these imply that Vz is only a function of r. And that should be obvious because we've said that the flow is invariant along z and the flow is invariant along theta. So whatever the profile will be, it resembles a parabola, a paraboloid rather. So it will be only dependent on, so this is the z direction, this is the r direction. So the velocity in the z direction will depend only on r. So these are what we can conclude right away. Now let us write down the r momentum equation. So the r momentum equation is as follows: rho del vr del t. Actually, I'll not write down the entire set of terms. I'll directly write it as d vr dt, and additionally there will be a minus v theta square. This should not be a vector. This should be, yeah, minus v square by r is equal to minus del p star del r plus mu Laplacian of u vr equal to 0. Not equal to 0. So the fact that all the terms contain vr, so we are not so much concerned with the form of the terms. So those equations will be provided in the examination. The fact that vr is 0, v theta is 0, vr is 0, that implies from this r momentum equation that minus del p del r is equal to 0, del p star del r is equal to 0. So if this is true, then p star is not a function of r, it is not a function of theta also. It is not a function of theta because of axis symmetry. And these considerations imply that p star is a function of z only. So now we can write down the z momentum equation. So the theta momentum equation is quite trivial. The theta momentum equation will simply imply del p star del theta equal to 0. In fact, this is 0 trivially because of the axisymmetric assumption in the problem. So now we can proceed and write down the z momentum equation. So let me write it down in its full form. So rho del vz del t plus vr del vz del r plus v theta upon r del vz del theta plus vz del vz upon del z is equal to del p star del z plus mu 1 upon r del r of r del vz del r plus 1 upon r square del 2 vz del theta 2 plus del 2 vz del z2. So because the flow is assumed to be steady, this term vanishes. Because Vr is 0, this term vanishes. No penetration. This term vanishes because of two reasons. The first reason is no swirl, and the second reason is axisymmetric. No swirl and axisymmetry. This term vanishes because the flow is fully developed. This term exists. This term vanishes because of axisymmetry. This term vanishes because of fully developed flow. So finally, we have 0 is equal to minus del p star del z plus mu 1 upon r del r of r del v z del r. And we've already seen that p star is only a function of z and vz is only a function of r. Okay, vz is only a function of r. So we can modify this equation as dp star dz is equal to mu 1 upon r ddr of r dvz dr. We can write this. So we've converted the partial derivatives into ordinary derivatives. Keeping in mind that this is only a function of z and this is only a function of r, each has to be then equal to a constant. Same logic that we had used in the plane Poiseuille flow. So now if each is a constant, it automatically means that the pressure varies linearly. So this implies that P star equal to, see if I call this as C, so it will be C Z plus C1. Okay, when I integrate this, I will obtain P star equal to Cz plus C1, and you can use the conditions that, so you want to find out these two constants. So P star at x equal to 0 you can call P left, P star at x equal to L, that is the length of the tube, you can call as PR. So using this you will find a linear decrease in the pressure. So if I plot the pressure, if this is PL, if this is PR, and if this is x equal to L, the pressure will linearly reduce. So correspondingly, this equation for the pressure would be P star equal to PL plus PL minus PR upon minus L times X. It's just a linear equation going from this point to this point. So at x equal to 0, you have PL, at x equal to L, you have PR. So this is the equation for the evolution of, not the evolution, for the spatial distribution of the pressure. So now if you compare, this should be Z, my bad, this should be Z, not X. Yeah. So if you compare these two expressions, the value of the constant comes out to be PR minus PL upon L. Okay. So now we focus our attention on the velocity distribution. Okay, so this is the velocity, the part which governs the velocity. So mu I can keep over here. So then what do we have? DDR of R d Vz dr is equal to CR upon mu. We can integrate this once and obtain R dVz dr is equal to C by 2 R square upon 2 plus C1. This C1 and this C1 are not the same, obviously. Now, before proceeding further, let's just look at the boundary conditions at the cylinder, the tube walls. So at R equal to, say, A, that is the wall of the cylinder, uz will be equal to 0, and this is a consequence of the no slip boundary condition. And at R equal to 0 you expect del uz del R to be equal to 0, and this del will actually be D, and uz has to be bounded. I mean, that's a condition we will quickly run into. So if we divide everything by R over here, this vanishes, this becomes simply R, and this becomes C1 upon R. So now we can integrate this one more time to obtain Vz is equal to C upon mu R square upon 4 plus C1 ln R plus C2. Now at R equal to 0, this log term blows up. It tends to minus infinity. So because the flow has to be bounded, C1 has to be equal to 0. And this kind of logarithmic blowups do happen often in the case of spherical coordinate systems and cylindrical polar coordinate systems. And it has to do with a completely different set of harmonics. But anyway, in this particular case, it is sufficient to know that for the flow to be bounded, so it's a boundedness condition, that this constant associated with log R has to vanish. Therefore, the velocity profile is simply C upon 4 mu R square plus C2. And if we look at the condition at R equal to A, Vz equal to 0, then 0 is equal to C by 4 mu A square plus C2. So this gives us an equation for C2 which we can substitute in the velocity profile to obtain Vz is equal to c by 4 mu r square minus a square, or we can write it down as minus c by 4 mu times a square 1 minus r square by a square. I've just rewritten this slightly differently, and recall that c is equal to dp star dx. C is equal to dp star dx. So essentially we can write down the entire formula in terms of this. So this is the velocity profile for a steady state, fully developed viscous flow through a pipe of diameter A. Now what is the maximum velocity? Quite naturally, the maximum velocity occurs at the channel center line, and so the velocity will be at r equal to 0. So Vmax will be a square by 4 mu dp star dx. This is the maximum. Have I written it x everywhere? It should be dz. Yeah, it's dz. So this should be dz. So with the help of this maximum velocity, we can write down Vz upon Vz max as 1 minus r square by a square. A very compact way of writing it. What is the volume flow rate? So the volume flow rate will be the integration of the velocity profile over the area. So 2 pi r dr divided by the area. So this goes from 0 to r, and you can easily find out that this comes out to be minus r square. Not, we have assumed it to be small a, not. Yeah. So it comes out to be minus a square upon 8 mu dp star dx. So yeah, I mean, all these are simple things, nothing very complicated about it. The shear stress, can be written as tau rz is mu del vr del z plus del vz del r, and this is equal to mu dvz dr. So you can find out this expression as well. I'm not gonna elaborate over the very pedestrian calculations. So the skin friction coefficient, so I'll just tell you the result. So tau wall is equal to r by 2 dp star dz. So the skin friction coefficient is defined as the magnitude of the wall shear stress divided by half rho u square, the v average square rather. So this is the average velocity. So you can do this calculation and you will find that it is equal to 16 upon rho vz bar d by mu, where d is the diameter of the pipe. So this comes out to be 16 upon Reynolds number based on the diameter. Once again, Reynolds number is nothing universal. You can define it on different length scales, but the most physically relevant length scale is this. So now from the average velocity, if we know the average velocity, okay, we know that the average velocity and pressure gradient are related by this. So with this in mind, we can integrate. So this average velocity is constant. Okay, it's not varying over r anymore. For some reason I'm using r instead of a. The radius is equal to a. So now we can integrate this to find out. We can integrate this expression to find out the pressure difference. So let us see. I mean, we know that it is PL minus PR, but what is the magnitude of delta P? That is of great importance. Okay. So VZ average times 8 mu upon A square, right? This is equal to minus dP star dz. And minus dP star dz, as we've already seen. So from this expression, it will be dP star dz will be PR minus PL upon L. Essentially, it is delta P. So delta P is PR minus PL upon L. So then delta P is equal to 8 mu V average times L upon A square. And if I want to write it in terms of the diameter, I multiply by 4. So this becomes 32 mu Vz bar L upon D square. So this is the pressure drop along the tube for a length equal to L. Now we can write everything in terms of the volume flow rate also. So the volume flow rate is this. We want to express this volume flow rate in terms of the average velocity. No, this was not the volume flow rate. In fact, this was the average velocity. This was the expression for the average velocity. So if you do the math carefully, the volume flow rate is equal to integral Vz into 2 pi r dr. So, I mean, okay. So the average velocity is simply the volume flow rate divided by the area. Okay. So we can use this over here. So the average velocity, if I want to write it in terms of this, so delta P, it comes out to be 32 mu. So Vz bar is equal to Q upon A. So A d square. But area is equal to pi d square by 4, right? So this becomes 128 mu Q L upon pi d raised to 4. Okay, so this is the relationship between the driving pressure and the volumetric flow rate. Okay, so this is the relationship between the driving pressure and the volumetric flow rate, and it is quite analogous to the electrical circuit where V equal to IR kind of. So I is the current and it is like the volume flow rate, V is the potential difference and it is like the driving pressure gradient. So the hydraulic resistance, okay, so this entire thing, so if I write L over here and this Q over here, so this entire thing is like the hydraulic resistance. Okay, so if we write the pressure drop in terms of rho g h, so h is called as the head loss. So the head loss is equal to 128 mu L Q upon rho g pi d raised to 4. Okay, and oftentimes head loss is empirically written in this particular fashion: F L by D times half rho V square by rho G. I mean, this can be simplified as V square by 2G. So F is a dimensionless sort of number. L by D is the aspect ratio and V square by 2G is the dynamic head. This particular term is the dynamic head. All right. So HF is 128 mu L upon rho G pi d raised to 4 times Q. This is equal to F L by D times Vz square upon 2G. Okay, so from this you can evaluate an expression for F, and F comes out to be 64 upon Re based on the Reynolds number. And this coefficient is called as the Darcy Weisbach formula. Okay, so from this we see that the Darcy Weisbach, the Darcy friction factor, it's also called as Darcy friction factor, is equal to 4 times the skin friction factor. We've just obtained that the skin friction factor is 16 by RED.